So now we have also predicted numerically. So we have taken a surrogate of liquid petroleum gas LPG, which is say 60% in butane and 40% propane. This is called surrogate of LPG. Okay. So when you try to numerically predict the so this is again detailed mechanism is used, detailed chemical kinetics is used to do this axisymmetric burner, then premixed reactants comes in and burns. So now the U average value of the unburnt reactant velocity is 0.6 meter per second, and the value of SL based upon the you can say the cone, half cone angle, etc., alpha, and you know U. So you calculate the alpha and try to calculate SL, that comes to about say 0.4 meter per second. And this is the basically equivalence ratio is unity, so stoichiometric reactant is supplied. Okay. And again 1 atmospheric pressure and 298 Kelvin or maybe 300 Kelvin is the temperature of the reactant mixture. So now this is the temperature contours. Contours means it gives the map of the temperature. So you can see that the white is over 400. So very low temperature prevails and the temperature increases here, and this is the burnt gas temperature, burnt gas, and this is the reaction zone basically. Okay. How is this reaction zone? Because we are plotting the net reaction rate of butane, it coincides with the net reaction rate of propane also. You can see this is the negative values you can see for consumption of butane. So butane is consumed here. So according to the consumption of butane, you have negative values, and you can see that butane is consumed here, and see the maximum value of consumption is -40, which occurs here and goes here. So this actually will give you the flame regime, and now the temperature contour is given here. So this is a stable flame. When you have a velocity of say 0.6 meter per second, I get a stable flame which is anchoring slightly away from the burner rim. So this is the burner rim here, correct? This is the burner rim, and here the burner rim. So slightly away from the burner rim, you can see that the flame is anchored properly. On the other hand, when I decrease U to 0.1, same scenario, same equivalence ratio, same mixture, decrease U, you can see that now this is the rim. Flame has come down, flame is propagating down, flame has come down, and you can see the this is the rim, flame has already come in. So you can see the dimension here. So the rim ends here, this is the end of the rim, so about 9 mm the rim ends basically. That is, so the burner exit is at 9 mm in Z scale, okay, whatever I put in Z direction, it is 9 mm. So now you can see that at the velocity of 0.6, the flame is over the burner rim, above the burner rim, burning slightly about 0.5 mm away from the burner rim, 1 mm away from the burner rim. On the other hand, you can see this is the burner rim, and the flame has propagated down here towards the zeroth, like the origin, and flame has propagated down, and reaction zone is formed right at the entry of the gas. Because velocity is so low, the unburnt gas velocity is 0.1 meter per second, flame speed is about 0.4 meter per second. So flame will not wait till the reactants reach that, flame has propagated down to consume the reactant. This is called flashback. So numerically there is no harm in doing this flashback studies, but experimentally we have to be careful. Now lift off. So I now abruptly increase from U 0.6 to 2.5. You can see that the reactants are going to enter at a very high velocity. It's moving the lifting the flame off, and the flame is lifted off now. Eventually it will blow off. Eventually this flame will blow off. Okay. Now we can see that the flame zone tries to move away. It cannot sustain the incoming high velocity. So that is the flame lift off. So dangerous. You can see that the reactants which is coming out can leak out, and the atmosphere air can come in this is the atmospheric air which is come in, and reactants can leave. Okay, incomplete combustion can occur, correct? There is no way you can sustain this flame easily. So liftoff is that that type of instability where there is no control provided from the flame. On the other hand, you can see the flashback is very dangerous because the flame tries to propagate down. Now if there is a mixing chamber here, okay, mixing chamber with reactants, it is very dangerous because it can ignite this, correct? So these are the two instabilities which we have to avoid. Okay, now the next is what is anchoring, how the anchoring occurs. Within the narrow range which we have talked about, the reactant flow rate, okay, the flame can be stable. Okay, how the stability is achieved? Small velocity fluctuations may be there. So small fluctuations in U can occur. If it occurs, that will not bother the flame. The flame can be perturbed, but again it will come and reach the equilibrium position. Once this range is violated and the velocity is increased beyond this range or decreased beyond this range, then there will be a instability. Okay, so now again we are concentrating close to the rim. You see this linear line, that the straight line here is the U profile, and this SL profile I am giving. Now I am wearing the SL profiles. In the previous case we did the other way. So now the equilibrium point where the flame is stable we are going to see. Okay, now figure shows the variation of U and SL along the radius profiles. Okay, now in position 1, what happens is the SL is smaller. So the any flow streamline is smaller than the reactant velocity U, and the flame is driven away by the blow gas. This you can see, this SL in any flow streamline is smaller than this. So the actually here the SL is smaller, here SL is again smaller. So if you take the local velocity here, the corresponding SL is smaller than that. When you resolve it, so either you resolve U to that direction or resolve SL to this direction, you will find that in the first position the flame, that means from a stable flame you are slightly increasing the velocity U, so that the flame is not able to match that speed of the reactants. So the flame is driven away from the gas. As the flame moves away, but it is not, so it is only small perturbation. So it moves away now due to the slight increase in the velocity, it just moves away. Now goes to position some position 2, where when it moves away the heat loss to the rim decreases. Similarly, the radical losses to the rim decreases, correct? As the flame moves away, the loss of heat and chain carriers are radicals, decreases, the loss decreases, so SL will increase. So now at this position 2, it will have sufficient amount of SL values to match U values. So position 2 is reached, that is the equilibrium position where locally SL matches the U value and equilibrium is reached, that is the flame will now sustain at that point. Okay, now what you do, you decrease the velocity now U, then the flame will try to go to position 1. Okay, so this is not discussed here, but we can discuss this. So from the position 2, if you decrease the velocity slightly, okay, then what happens is you go to a position 1 now. Okay, now when the flame reaches the rim, it will lose more heat and radicals. Then what happens? Its velocity SL will decrease. So now at this point U will be more than SL. So again you will push the flame out to position 2. So again it will reach the equilibrium position. Now let us take the other condition when the U is again increased more. So when if the flame is pushed up to a larger distance, say position 3 by perturbation of the U to a higher value, then SL at the indicated point, okay, 3 becomes larger than U. Why? Because it will SL will increase because it will lose lesser heat and radicals to the wall because it is away. Now what happens, the SL will increase, so it will try to come down again to the equilibrium position. So whether the flame from, this is the equilibrium position, 2 is the equilibrium position, from that if you decrease the velocity it may go to position 1 where the SL will decrease due to the increase in the heat loss and radicals, then due to mismatch between U and SL it will again go to the position 2, which is the equilibrium position. When it is lifted off to position 3, again due to the reduction in the radical and heat losses, SL will actually increase and now try to come down to the position 2. So when we operate the burner in a small range of velocities, then we always have the flame within this position 2, which is the equilibrium position. The flame anchors at position 2 stably. So, but if you increase or decrease velocity more than this range, then we are not going to get a stable flame. Either it will flash back with the velocity is reduced too much, or it will lift off, the velocity is increased too much. So the flame stability maps, this is very important to do for all the burners. When you have a burner with premix reactants, so we have to select first fuel, then range of equivalence ratio, then TU, unburnt this range, then see fuel also know the then range of flow rates. So this you have to first fix. So that will be range. Why this range of fuel flow rates is required, fuel and air flow rate, range of phi, because you have to have a range of power produced by the burner. So when you fix this, we have to draw a map like this, which is called flame stability map. What we try to do here is, we try to, the fuel input rate is given, okay. We can also put fuel input rate or power rating here, power, which is nothing but fuel input rate into delta Hc or calorific value. Then you get the say joule per hour, okay. Okay, so that is what we can plot here. So this is a range of operation we should decide on first. Similarly, for the fuel flow rate, we have to supply air. Why I call primary air is because normally in a big combustion there will be stages of combustion. So we will have primary air, and we will also have some secondary air to cool the hot products and so on. So secondary air, tertiary air, zonal air will be supplied. So primary air basically is the air which we supply along with the fuel. So that is called primary air. So this is actually calculated percentage theoretical. Stoichiometric is 100%. So whether it is 80% stoichiometric or 120% stoichiometric, etc., it will vary like this. So now if you see, if you have a mixture which is ignitable mixture, and there is a fuel flow rate and air flow rate, but the velocities are low. If you have in this, the velocities of the mixture is very low. So for the given equivalence ratio, etc., the flame velocity will be higher, flame speed will be higher. So flashback occurs. So you note these points where flashback occur and put a boundary like this. So to the left of this boundary, flashback will occur. So I should not go to this. Similarly, I note the points where the liftoff initiates and draw this line, which is boundary, which will avoid see crossing this boundary for a given fuel flow rate and air flow rate. If I am here, surely it will lift off. For a given fuel flow rate and air flow rate, if I am in this point, it will flash back. So I should not go to this. So similarly, when I don't provide enough air, then yellow tipping will occur. Yellow tipping is the will occur in a fuel rich mixture. Okay, when you increase the phi value, equivalence ratio value, say 2.2, 2.5, etc. Yellow tipping, that means that yellow tipping indicates that there is a probability for incomplete combustion, because some CO can be released or soot can be formed in some fuels and so on. So in some fuels, in all fuels it not occur. In some fuels like LPG, etc. higher order hydrocarbons, unsaturated hydrocarbons, yellow tipping can occur if you starve the mixture with too much of air, starve the mixture with air, or supply too much of fuel. So this also you avoid. So now this is the range you have to operate, but normally we take a stable range. This is the range which we take, and I call this a design area. So now I will only supply fuel in this and air only in this range, so that I get proper stable combustion. So this stability map has to be done for different fuel type. This for a given burner you have to check it. When in a given burner itself, if you want to change the fuel from methane, natural gas, say to LPG, you have to conduct this experiment and get the map and get this design range of operation. Okay, so this is very important. Okay, so this is the end of the topic. Let us see a worked example. Okay, worked example: a cylindrical tube burner. Okay, diameter of the burner is 5 centimeter tube. This diameter of the tube is 5 centimeter. Is supplied with a premixed mixture of butane and air. The volumetric flow rate is 15.5 liter per minute, and the volumetric fraction of butane is 0.025. Okay, 0.025. Now the laminar flame speed in centimeter per second may be estimated using the correlation, which is SL equal to 34 minus 139 times phi minus 1 the whole square, where phi is the equivalence ratio. Okay, now it is ignited somewhere. Okay, it is ignited somewhere and the flame is formed. Determine the direction and the velocity of the flame propagation. That is what we need to find. So now for this, so determine the direction and the velocity of the flame propagation. So 1 liter per minute is equal to 1.66667 times 10 power minus 5 meter cube per second, SI units. Convert that. So the flow rate is 2.54 into 10 power minus 4, corresponding to 15.5 liter per minute. It is 2.58 into 10 power minus 4 meter cube per second. So reactant velocity is nothing but the flow rate, volumetric flow rate divided by the area of cross section, which is 2.58 into 10 power minus 4 divided by pi d square by 4. So that is 0.1314 meter per second. So U is 0.1314 meter per second. Now what is phi? When I want to calculate SL, I need value of phi as per the correlation. What is phi? You know the reactant mixture is butane, 1 kilomole of butane plus A kilomole of the air, that is A kilomole of oxygen and 3.76 times A times nitrogen, okay, kilomoles of nitrogen. So now what is given is the volumetric fraction of butane, which is the mole fraction of butane. So number of moles of butane is 1, total number of moles is 1 plus A plus 3.76 A. So 1 by 1 plus A plus 3.76 A will be the mole fraction of butane given as 0.025. So from this A value is estimated as 8.193. Now stoichiometric value of A is 4 plus x plus y by 4. So 4 plus 10 by 4 is 6.5. Now from this stoichiometric A value, you know, actual A value is 8.19, stoichiometric A value is 6.5. So what is the phi? Phi is close to 0.8. So once you know the phi, calculate SL in centimeter per second, convert into meter per second, 0.2806. That means the reactants are flowing at this, and the flame is formed here, and the flame propagates with SL of 0.2806, so that the reactants are coming at a speed of 0.13, and the flame can propagate at a speed of this 0.28 meter per second, so that the flame actually will propagate in the direction opposite to the mixture at a velocity of 0.15 meter per second. So this is the first example where you use a correlation to find the SL value. Second example, a stoichiometric mixture of butane and air is kept at 1 bar and 300 Kelvin in a long open cylindrical tube flame temperature is given as 2200. It's an approximate. You can find the adiabatic flame temperature. The molecular weight of the mixture is given as 30. Thermal conductivity and the specific heat is given as 0.04 and 1500. Okay. Down the reaction rate in the consumption of butane. So negative is because of the consumption of butane is also given here. This is the A value. This is EA by RU value, and this is concentration of butane power M, concentration of oxygen power N. So single step reaction. So what is the flame velocity or the laminar flame speed? So this is actually stoichiometric mixture. So write the equation for the stoichiometric mixture like this. This is what is taking place. Now you know that this is the reaction zone, and in the simplified analysis you use this. So this is x equal to 0, this is x equal to del, and this is say Tu, and this is Tf, correct? So linear variation. So now please understand this important calculation of temperatures, average temperatures, etc. is very important here. So this is the reaction rate which is given, but the reaction rate or the concentrations at what temperature you will calculate. For that, what we assume is this is half of the reaction zone. So we say that the reaction takes place between del by 2 and del, obviously because in our simplified analysis we assume that minus infinity to del by 2 no reaction takes place. So predominantly reaction takes place between this point which is del by 2 and del. Okay. So what is the temperature between this? You know this is a linear profile, linear variation of temperature. So this point the temperature will be Tf plus Tu by 2. So this temperature is T del by 2 equal to Tf plus Tu by 2, and here this is Tf. So the average temperature here is Ta, which is nothing but Tf plus Tu by 2, both added up and divided by 2, that is 1725 Kelvin. That is the average temperature at which the concentrations are evaluated and the reaction rate is calculated. You can also calculate the temperature, the reaction happening at Tf, but obviously reaction has started well before that. So you have to take some average temperature. We are requiring only the average reaction rate. Maximum reaction rate will be Tf, what we calculate Tf, but we are now interested in the average reaction rate. So which is calculated at this temperature. How to calculate concentrations? Now I calculate initial concentrations. Initial concentrations are, we know the partial pressure of butane, that is the mole fraction into total pressure. Total pressure is 1 bar. So mole fraction of butane, this is x butane into 1 bar. So that will be the partial pressure of butane. Similarly, partial pressure of oxygen, you calculate that. What is concentration? Concentration is P by Ru into T. So this is the, again when you do calculate the concentration, as I told you, you have to take the average temperature which you calculated here. The flame zone average temperature, this temperature you have to take, that is 1725 Kelvin. So use that temperature here to calculate the concentrations of this. This is initial concentration. Okay. So we can also assume that concentration also varies from a high value to a low value linearly. Okay. So reaction rate is calculated using average concentrations and average temperature. So initial concentration, say for example, this is del by 2 and this is del. The concentration, initial concentration is this. Concentration falls to 0 here. So this is 0, 0, and this is initial concentration. So from initial concentration, the reactants concentration decreased to a 0 value. So what is the average concentration? Average concentration can be taken as half of the initial value, because this concentration plus 0 by 2. So half of the initial value, assuming linear variation. So temperature also we have assumed like this, it increases linearly, concentration also decreases linearly from initial value to a 0 value. So average concentration is half of the initial value. So using this half of the concentration for the initial concentrations which is subscript 0, then you can calculate the reaction rate in kilomole per meter cube second or in kg per meter cube second. So now you have to find the S, 1 kg of fuel, 1 kg fuel plus S kg oxidizer giving 1 plus S kg products. So, what is S? This S is nothing but the mass of air. So, that is 6.5 A into, for this stoichiometric reaction, into 4.76 into molecular weight of the air divided by the molecular weight of the fuel. So, for 1 kg of fuel you need to require 15.4 kg of air, that is value of S. For 1 kg of fuel you require 15.4 kg of the oxidizer, which is air. So, now that you calculate. Then similarly, mixtures specific gas constant, universal gas constant by the molecular weight of mixture, which is given as 30. Similarly, calculate the unburnt reactant density, which is required for SL. Similarly, the average density for which you are going to calculate the value of alpha. So, the average value now is entire reaction zone. This is x equal to 0, this is x equal to del. In the entire reaction zone, what is the average temperature here? This is Tu, this is Tf. So, what is average temperature? Tf plus Tu by 2. That will be the average temperature in the entire reaction zone. At that temperature, average temperature, calculate density, calculate the value of alpha, because the K and Cp value are given at average temperatures. Okay. Now, this is the thermal diffusivity. So, substituting all this, you get SL as 0.473. You are over predicting this. Okay. So, this is the way you calculate the SL based upon the simplified analysis. The main important point to note here is the values of the properties have to be evaluated at a from average temperature. So, similarly, the reaction rates, concentration of the reactants have to be calculated at some average temperature, which is very close to the reaction zone, okay, and so on. Okay, so this we will stop this now.